So let us go through this test tomorrow. First off, identifying physical or chemical changes. Remember, there are 6 basic physical changes involving change of phase, melting, boiling, vaporizing, condensing, freezing, and strictly speaking, something we haven't really talked about much, but soda pop bubbling is essentially a physical change. The bubbling is basically CO2 gas that's just coming out of solution. It's really not changing form. The key to a chemical change is it has to change form. It has to produce something new. We have 5 indications of a chemical change: produce color change, produce a temperature change, produce a solid, which we call precipitate, produce a gas, and produce light. So things that would fall under there as well would be tarnishing. That would be a chemical. Silver tarnishes, turns kind of blackish. We have oxidation, which is essentially what rusting is all about, and tarnishing and so forth. And so there you have all of 1 done. 2, how is a chemical change different from a physical change? Well, the big key is new properties. That's really the key. A compound is formed with new properties. Okay? So we form a compound and it has new properties. Lots of examples. We could have hydrogen and oxygen gases, which turn into water, which is a liquid, so at room temperature. So that could be an easy example. You have also sodium metal and chlorine gas, which when you put them together you get table salt. 2 things that would not be good for you, but combined is something you need for your health. Okay, number 3, hydrogen gas reacting with oxygen produces water and a little energy release, leads to 2 properties of H2, O2, and H2O. Well, we've already listed 1. These are gases. So that would be 1 property. Now, since they are gases at room temperature, that means that their boiling points have to be pretty low. I mean, boiling changes something from a liquid into a gas, and they're already gases at room temperature, so we don't need it to be very hot for those gases to be gases. Water, on the other hand, which is a liquid at room temperature, has a relatively higher boiling point. So that would be an example of those things. Melting points, of course, would have to be similar. Hydrogen and oxygen gases would be still gases at 32 degrees at freezing, but water would then freeze. So their freezing points have to be even lower than the freezing of water. Okay, now I've already answered 4 here up above. Does a compound have the same properties? No. And a different example than water, but would also work, is we can take H2 and O2 and turn it into H2O2, which is hydrogen peroxide. That would be another example. And hydrogen peroxide is clearly not the same thing as water. So again, coming back to that, a new compound has different properties. Hydrogen peroxide is the stuff, of course, that we can use as a disinfectant. Can sting a little if you have a cut. Bubbles, actually dissolves, breaks down blood. Say if it was on the carpet or on a towel, whereas water might just dilute it but doesn't really clean it out. Okay, draw and label an atom. Well, the simplest thing is if we take, say, helium, which is number 2, okay, and it would have 2 protons and 2 neutrons in its nucleus. So that part would be the nucleus. And then, of course, outside of that, it has to have its electrons. Since it's number 2, it's only got 2 electrons. Okay, and then they are in a shell. Notice that I put the charges for all of them. The protons are positive charge, the electrons are negative charge, neutrons are neutral. Protons and neutrons in the nucleus, electrons not in the nucleus. Okay, if we go to any old atom, and by the way, this was number 2, helium, it's number 2, so that's why we have 2 protons, 2 electrons, and because its mass is 4, that gives us 2 neutrons. So continuing on, what if we have something else and we need to figure out protons, neutrons, electrons, etc.? Well, for protons, all we got to do is look at atomic number. Well, atomic number is the smaller whole number, which for gold here, that's the atomic number. And so in this case, 79. Likewise, protons, 79. Notice that protons and electrons are both 79. If we round gold's atomic mass, note here the 9, we want to round to a whole number, so that would be 197 for its atomic mass. Remember that that's not one atom, but 6.02 times 10 to the 23rd atoms, which is also called a mole. How do we get the neutrons? Well, we take that rounded atomic mass and we subtract the atomic number. And we get 118 neutrons. Now, if we wanted to round gold's atomic mass to 1 or 2 decimal places instead of to a whole number, decimal places are the places after the decimal point. So, for instance, that would be the first one where the 9 is here. The 6, the first 6 would be the second one. We always look at the number afterward. Following the 9 is the 6. That's past halfway, so we would round the 9 up. So this one would round to 197.0 for 1 decimal place, and 196.97. And of course, again, always put your units in grams. Explain why the nucleus of an atom is relatively heavy, massive. Well, we ignore the electrons. They're so small, and all the protons and neutrons are in the nucleus. So all the mass, pretty much, of an atom is in its nucleus. Likewise, the shell or shells, because if you go past the first row, you've got shells. They just have electrons. And very little mass. Basically 1,800 times less than a proton. As I mentioned in the notes before, for 13, it says compare the size of an atom, its nucleus to its shell. That's sort of like looking at a solar system and its sun. You know, here would be the nucleus, and then, you know, way out here would be the shells. So nucleus, looking very tiny, and then shell. So most of it is empty space. And 14 basically goes back to what we did in 9. So round atomic mass to a whole number. And that means don't truncate. That means actually round up or round down, depending on what follows the decimal point. And then subtract atomic number. Okay, neutrons has to be a whole number. You cannot have a 10.8 neutrons. It's got to be 11 or 10. It cannot be something in between. Okay, our pictures here refer to 2 isotopes of helium. Notice this says helium-3. We have 3 particles in the nucleus. This one's helium-4, 4 particles in the nucleus. Helium is always number 2. Notice we have 2 dark ones here and 2 dark ones here, so automatically these are the protons, and this one is the neutron. And then helium-4, which of course again has its protons and neutrons. Notice that it has 1 more neutron than the helium-3, which is the difference from one isotope to another. Okay, they have the same number of protons, but they do not have the same number of neutrons. They have the same number of electrons too. Electrons don't change. Okay, what is the atomic number of helium? Again, it is 2. It is the second one on the periodic table. Which circle represents the neutrons in the diagram? They are the white ones. Okay, and again, to explain, if we think in terms of mass, all right, right there, that's the mass number. Same thing here. That's the mass number. So neutrons equals mass number subtract atomic number. So here it would be 3 minus 2 is 1. Over in the second one, it would be 4 minus 2 is 2. So that explains how we have the number we do. Isotopes of elements have the same number of the electrons and the protons, but have a different number of neutrons. And yes, I could have spelled all those out, but I'm reinforcing the charge for all of them. The mass of the nucleus comes from its protons and its neutrons. Any questions so far? Surprisingly, as I mentioned the other day, the stuff we've covered, almost no math here, and yet we did not do very well on this part on the quiz. All right, continuing. Weight is a measure of the pull of gravity. Mass is a measure of the matter in an object. So, even though it's not asked here, this one changes on the moon. Mass doesn't change. A lot of people said they both change. Mass does not change. You don't get any smaller. You weigh a lot less, but you don't get any smaller just because you were to go to the moon. Grams is a measure of mass. Milliliters and cubic centimeters are a measure of volume. And the gram per milliliter or gram per cubic centimeter are a measure of density. And here you have a little diagram that could kind of help you with the different types of problems. Almost everyone was okay on the density equation problem of the quiz. Density is mass divided by volume, but a number of people kind of fell down on the other two. This shows you all three versions, and what you can see, of course, is that when you're solving for volume, that's a division. You're solving for density, that's a division. But when you're solving for mass, that's the only one that is a multiplication. Likewise, if you look at the units, they also give you a clue, because in the density, the mass is in grams. The volume, say, is in cubic centimeters, which is our density unit. When we're looking at mass, we want grams. Well, density is grams per cubic centimeter, and then you go times volume, which is cubic centimeter. Notice that the volume units will cancel out, and we just have grams left, which is what we would want for the mass. And then here for the volume, we would have, we want cubic centimeters, Okay, well, the mass is simply going to be grams, and then you're going to divide that by grams per cubic centimeter. The gram parts will cancel. Since that's 1 over a cubic centimeter, we're left with that. So looking at the units can also give you a clue as to what has to be divided by what. Okay, 180-pound astronaut lands on 2 planets. On planet Obi-Wan has 2.3 times the gravity, and the other planet Jar Jar has 0.4 Earth gravity. What's the astronaut's weight on both of them? Okay, well, we're going to use a little bit of alteration here just so that we can keep things in pounds. Our weight equals the mass times the gravity factor. So using our gravity factors here of the 2.3 and the 0.4, our 180 pounds times the 2.3, that's our factor there, would get us up to 414 pounds on planet Obi-Wan. Higher gravity, higher weight. On the other hand, on the other one, our 180 pounds times only 0.4 for planet Jar Jar, and we're down to 72 pounds on Jar Jar. We did not, as I said before, get any smaller. Okay, I went on a diet, I got a lot smaller. Okay, because I literally lost mass, but simply going to a different location, all that can happen is the gravity could be different and you could be heavier or lighter. Okay, 23, we had this question on our quiz. What's the box's volume? Remember that volume is length times width times height. So in this case, 4.3 centimeters times 35.5 centimeters times 10.1 centimeters. Multiply those all together. And it looks like we get 1,541.765 cubic centimeters. However, it says round to 1 decimal place. Again, the decimal places are after the decimal point. So we would want to round the 7. We look to the number afterwards. That's above 5. So this would round to 154.8 cubic centimeters. Okay. Now, question 24 refers to question 23. We want the box's density. Again, density is mass over volume. You can refer back to that diagram. Now, you will have the density equation. You won't have all 3 on the test, but you will have the density. These 2 are just that one rearranged. But there is the density equation. We have our mass here of 430 grams. Again, grams on top. We use what we had below, above in question 23, 1541.8 cubic centimeters. And that gives us a 0.278, and then there's a whole bunch more digits. No, we don't need to write them all down. Density again, grams per cubic centimeter. There's my grams, there's my cubic centimeters. It says round to 1 decimal place, so that would be the 2 spot. It's followed by a 7, which is greater than 5, so this would round to 0.3 grams per cubic centimeter. Question 25, we have 3.1 gram samples. So first of all, please note this is mass, because it says gram there, of aluminum, which has this density, iron, which has that density, and gold, which has that density. Calculate their volumes and list an order of increasing volume. Round all answers to 2 decimals. All right, so we want their volumes. So looking up at our triangle at the above, volume is mass times density. So for the aluminum, we'd have the volume is, again, the 3.1 gram times the 2.7, excuse me, yeah, I went and screwed it up. Divide. Volume is the divide. Mass is the only multiply. Now you might, even though I made that mistake, notice I caught it right off the bat, because once I started actually writing my numbers with their units, I noticed if I was doing multiply, I would have had g times g, which is not going to work. There's no g squared unit. I'm like, wait a minute, that has to cancel, and that reminded me that this is actually a divide. So I started to make the mistake, but once I paid attention to the units and realized, hey, volume, it's got to be just in cubic centimeters, no grams in it anymore, I realized that this has to be mass divided by density, which in this case, 3.1 divided by 2.7 gives me 1.148 cubic centimeters, which would round 2 decimal places in this case to 1.15. The 4 is in the second, it's followed by an 8. For the iron, RV is still 3.1. All of them are 3.1 in this example, but now we're going to divide by 7.9 grams per cubic centimeter. And so we get 0.392, which would be approximately 0.39 cubic centimeters. And then our gold, which is a very heavy metal, notice how much higher its density is than the other two. Aluminum very light, gold very heavy. So that goes along with their densities. Let's see, we got 19.3 grams. And so this one comes out 0.1606 cubic centimeters. To the second place is that first 6, so that would be 0.16. It wants us to list them in order of increasing volume. So that would mean this one here would be the first, then second, then third in increasing order. So the aluminum would be the one with the biggest volume. The gold would be the smallest volume. Now 26 is similar to 25, except this time, notice 5 cubic centimeters, we have a volume with our 3 densities, and they want the masses. And mass is the one that's a multiply. So mass is the density times the volume. So for aluminum, it would be density 2.7 grams per cubic centimeter times the 5 cubic centimeters. Notice how the cubic centimeters go away and we're left with just grams. And we get 13.5 cubic centimeters. For the iron, same thing, 2.7 grams per cubic centimeter times the 5 cubic centimeters. Oops. 7.9 for gold, iron. Got to writing too fast. And so this one is 39.5 cubic centimeters. And for the gold, we have our 19.3 times the 5. So that one has 96.5 cubic centimeters. So please note, in this case, for the same volume, the higher the density, the greater the mass. So in this case, aluminum has the smallest mass. Now, did anybody? Nobody said a word. Did anybody notice what I did wrong there? What did I do wrong?
Didn't you put cubics?
Yeah, I did. These are all grams. That's correct. Got to pay attention to the units. I canceled out my cubic centimeters. I'm supposed to be in grams for mass. Probably looking at the problem right above it and just accidentally just kept writing the same thing. Okay, yes, they have to all be in grams. So the biggest grams was the gold. And yet, in the previous one, it had the smallest amount of volume. Okay, 27. I have a 7,000 gram chunk. Again, that's mass. Density is 0.3 grams per cubic centimeter. Calculate its volume. Again, volume is the mass over the density. So my mass, 7,000 grams over 0.3 grams per cubic centimeter. And boy, this is a big volume. $23,000 cubic centimeters. Of course, it's a big chunk of pumice, so it's probably not something we have in the room. Okay, 28. If you have 219 cubic centimeters, so this is a volume of frozen lava, and there's this density. Calculate its mass, and again, the mass is the density times the volume. So in this case, our density, 3.2 grams per cubic centimeter times the 219 cubic centimeters. And it gives us 700.8 grams. Now 29 is a density equation. So density is mass over volume. This, milliliters, that's a volume. And here it says mass of 1,050 grams. So this is 1,050 grams over 300 milliliters. And we get 3.5 grams per milliliter. Now, question 30, we start to do conversions of units. Let's go back for a moment before we continue. On the first page at the top, we have different conversions from one unit to the next. We need to use the appropriate one to be able to do a conversion. The same thing will be true on a test. You will have the density equation, and then you'll have these particular conversions that you might need. So, first of all, 30 says how many centimeters are in 600 meters. To do that, we need to use the conversion that 1 meter is 100 centimeters. And then we write down what we want to change. Notice how I put the multiply sign and drawn the line. Whatever's here goes underneath. Okay? The other part goes on top. So the centimeters is on top because I'm changing it into the centimeters. The meters gets canceled, and I'm left with 60,000 centimeters. Now, how many miles is it? Well, I'm assuming that's our 600 meters. And in this case, if we go back to the other page, we could use that 1 mile equals 1.61 kilometers, which is also, let's see, and we have 1 kilometer is 1,000 meters. So we actually would need to do 2 changes. So first off, 600 meters. Let's change that into kilometers. Since that's meters, now I have the meters down at the bottom, my 1 kilometer on top. And now we can change our kilometers into miles. The 1.61 kilometer would go down here, and the 1 mile go up there. So notice meters here, meters down there, kilometer up there, kilometers down there. Now it's easy to tell whether it's multiplies or divides. So we've got 600 divide by 1,000 and then divide by the 1.61, and it ends up being about 0.373 miles. So 600 meters is a little bit more than 1/3 of a mile. Okay, 31. How many meters are in 60 centimeters? Okay, we've already got that conversion. 1 meter is 100 centimeters. So again, we always start with what we want to change. So there's the 60 centimeters. Draw, multiply in the line. Now we're going to put the 100 centimeters on the bottom, the 1 meter on top. What we wanted to end up with was on top, 60 divided by 100, 0.6 meters. Okay, grams into kilograms. Well, there are 1,000 grams in 1 kilogram. Remember, there's no unit K. K is a prefix meaning 1,000. So kg, that's 1,000 grams. Up here we had km, that's 1,000 meters. The K is a prefix to whatever our measurement is. But same idea, 60 grams. G's here, so G has to go down here. The 1 kilogram goes up there. 60 divided by 1,000, 0.06 kilograms. They want us to convert that into pounds. Well, it turns out that 1 kilogram, and again, this is on the first page, is 2.2 pounds. So we can take our 0.06 kilograms, 1 kilogram on the bottom, 2.2 pounds. And we end up with 0.132 pounds. Now all of this probably looks pretty easy with me doing it here, okay? But you have to be able to do this yourself. Okay, so not only would I go over this as you're reviewing for the test, but I would look at the rest of your homework, which was those metric conversions, and I would go back to the worksheets where we did conversions to give you more examples. You could even rework them out to make sure that you were getting the right thing. Okay, milligrams to kilograms, so that's 2 changes. There are 1,000 milligrams in 1 gram, and there are 1,000 grams in 1 kilogram. So, start off with my 6 million milligrams, and then times, let's change it into grams. The 1,000 milligrams goes down here, the 1 grams goes up there. Notice milligrams will be canceled leaving us in grams. Then change it to kilograms. And since grams is up on top, the 1,000 grams has to be down there at the bottom. So now it's the grams that get canceled. And our answer is 6 kilograms. If we want that in pounds again, we've got the 6 kilograms times 2.2 pounds per 1 kilogram. And that's 13.2 pounds. If you're 51 inches tall, how much is that in centimeters? Okay, well, it's 1 inch equals 2.54 centimeters. So we go 51 times, draw my line, put the 1 inch on the bottom, the 2.54 on top, and we get 129.54 centimeters. Now, how tall is that in millimeters? Well, 1 centimeter is 10 millimeters. So basically it's 129.54 centimeters times 10 millimeters per centimeter, which will equal 1,295.4 millimeters. Okay, for soda, it's 1 ounce equals 29.57 milliliters. So 16. Notice I'm doing the same thing every time. What I have to begin with is what goes first. I look at the ounces, OZ here. So the ounces, OZ goes down there. The 29.57 goes on top. And I get 1,774.2 milliliters. Here, I'll give you a big, not for me, but it might be for you. Now, some velocity related questions. 10 minutes to walk 1.5 kilometers. What is this in kilometers per minute? Well, notice that's kilometers, that's minute. So basically you're doing 1.5 kilometers in 10 minutes, which is going to be 0.15 kilometers per minute. Now, the next one says, how fast is this in kilometers per hour? Well, there are 60 minutes in an hour. So we take our 0.15 kilometers per minute times, now the minutes is down, so the minutes has to be up, and the 1 hour down, so that the minutes get canceled and I have kilometers on top and hours on the bottom. So 0.15 times 60 gives me 9 kilometers per hour. So next we have miles per hour. And again, 1 mile equals 1.61 kilometers. So I take my 9 kilometers per hour. Kilometers on top, so it has to be on the bottom, and the 1 mile on top. So the kilometers get canceled and I'm left with miles per hour. So the 9 is divided by the 1.61, which is 5.59 miles per hour. And then the last one, change that into feet per second. Well, 5,280 feet, 1 mile. And We also have 3,600 seconds in 1 hour, 60 minutes and 60 seconds. So change the miles. 1 mile down here, the 5,280 up there, and then I'll jump down here. Change the hours. So the 1 hour is on top to cancel with that 1 hour. 3,600 seconds is down there. And what do we get? 5,280 divided by 3,600. And we end up with 8.2 feet per second. Okay. Now, one last thing I'd like to show you. I know that was kind of fast for some of you, but it turns out if you go to YouTube